Recording is rolling on Thursday, September 16th. So to start you out with a couple of free body diagrams. Yesterday I was taking you guys through a free body diagram PowerPoint, which has been posted to Google Classroom. And also I gave you guys some notes on friction. So this is going to be a review of both of those things. And then today we'll look more at some free body diagrams, and I'll tell you guys a bit more about forces. We'll look at Hooke's law, which is involved in these spring scales. Okay, so that's all coming up. So what do we got here? Draw a free body diagram for two different situations. The situation on the left, I got a driver brakes and the wheels lock and the car skids to a stop. Right? This would be the old-timey cars, let's say a car from the 1970s, versus the one on the right, the scenario on the right, is like a new car. The driver brakes and then an anti-lock braking system activates and the car rolls to a stop. When you guys got your driver's licenses, did you guys have to learn about anti-lock braking system? You guys have to learn about that? Okay, yeah. I've been asking my other students today, and I've got some yes and some no. So, I'll tell you what this is about, or what the physics is behind this. So, the old-timey cars, let's say a car from a few decades ago, you were recommended to, what I'm about to tell you guys, don't do this. But the old recommendation was, if you had to stop in a hurry, don't slam on the brakes, but to pump the brakes, kind of ease on them. Okay. And the idea was that you would not want this to happen. You don't want the wheels to lock and the car to skid. Why would that be? Because there's actually a different kind of friction that you can take advantage of that will actually stop the car faster. You guys remember from yesterday, static friction versus kinetic friction. So there was both those notes. Yeah. You guys might remember I was telling you guys there's actually two different kinds of friction. There's what's called static friction and kinetic friction. This is your notes from yesterday. And the coefficient of friction relates friction force to normal force. So those will be the three vectors that you guys draw are going to be like weight, normal force, and friction force. Okay. But these frictions have different values. So I had you guys draw this graph. So what is the coefficient of friction? Say is a function of the speed of the two surfaces sliding past each other. Well, if the surfaces are not sliding past each other, let's say they haven't broken the initial friction, you can get a static friction situation. Once they are sliding past each other, then it actually jumps down. And kinetic friction is actually less than static friction. And if you were braking in a car, well, you wouldn't want, if you could take advantage of static friction, that would be more friction, wouldn't it? You get like a better friction ratio of friction force to normal force. But a car that's skidding across the surface, well, that's a kinetic friction example, isn't it? So I made up some example numbers. So let's call coefficient kinetic friction like 0.5, something like that. Right? Versus the new cars, any new car you buy almost for sure has anti-lock braking system built into it. This is a computer system that will actually rotate the tires forward a little bit as you're braking. So the new recommendation is don't pump the brakes, go ahead and slam the brakes, and then the system will take over and it will roll the tires forward a little bit. Hold on, how does that help brake the car faster for the wheels to actually rotate forward a little bit? Because if those tires can get traction with the road and actually not skid across it, but actually get traction, then you can actually go from a sliding friction case to a static friction case, which is actually more friction, which helps slow the car down faster. Okay. Great. Were you guys able to draw up the free body diagrams for each one of these while I was doing attendance? I'll take you guys over the answers. So the situation on the left I'll call coefficient of kinetic friction 0.5. And the situation on the right I'll call coefficient of static friction 1.0. Okay. Now I just made up these numbers. Kinetic friction will be less than static friction. Maybe more realistically, it might be like 0.6 and 0.7 or something like that. But let's do a free body diagram for each one of these cars. These cars roll into the right. So think about the rules for free body diagrams. There's free body diagrams. You're going to label what kind of forces, or sorry, what kind of vector. You guys are going to say forces, right? Force vectors. Right? So we're going to do a bunch of those. We did a bunch yesterday. We're going to do a bunch more today. Okay? So there's a convention for drawing these. You put a center mass dot on the object, and then just label all the force vectors extending from that center mass dot. So car on the left, say it has a weight that's pulling it straight down. No, I'll do both cars. We'll do in tandem. So the car on the right, let's say it has the same mass and therefore the same weight. You guys remember mg is the weight of the car. You guys remember that? Mg is weight. You guys did that last couple days. Now, if that's all you drew, if you just drew the weight vector and then walked away, then what would you be saying that those cars are doing? They'd be in what? A state of like free fall, right? Kind of like you drop these off a cliff. Maybe these cars would have been like flying off the edge of the cliff, like going over the edge, all dramatic, explosion at the bottom, right? But that's not what's going on. What's going on is there's a road that's surface that's holding those cars up. Do you guys remember what the name of this force is that's holding the car up? Normal force. Yeah, normal force. So I'll label this F sub n for normal force. Normal force. And what does normal mean again? Like if two lines are normal to each other, that means they are what? Perpendicular, right? So the name of this force literally is the perpendicular force. Perpendicular to what? Perpendicular to the road surface. Okay? So we have a level horizontal road going on here, so nothing fancy, but later on we'll go to inclines, and then this will still be the case. This is perpendicular to the surface, right? But it's not that get too far ahead. Right? So if the car is going at constant velocity, then that might be a pretty good free body diagram right there. Right? But these cars are braking to a stop. Now, remember, the car on the left is an old 1970s car. It's going to skid to a stop. And the car on the right has anti-lock braking. And it's going to roll a little bit, which is actually a good thing. It's going to help the car stop faster. Now, if you guys look at those coefficients of friction, then you can draw correctly to scale what the friction forces look like on these free body diagrams. Okay? That's what FBD stands for, right? Free body diagram. Did you guys do that? Okay. And what you should have done for, say, the one on the left, let me try as best I can to draw this to scale. Probably about like that. I'll call this friction force. And the one on the right, the car on the right, probably pretty close to that right there, friction force. Now look at those two friction forces. Ooh, you see the one on the right is a lot longer? Okay. How did I know to make it that magnitude and the one on the left to make the really short magnitude? Because if you look at this ratio right here, and the coefficient of friction is a ratio, right? It's the ratio, go back to yesterday's notes, remind you guys exactly what ratio this is. Well, got notes here, right? So this coefficient of friction. So if you divide normal force over, wouldn't it be friction force divided by normal force? Oh, I've got it right here. There you go. Here's coefficient of friction. It's defined as this ratio. Okay? And if it's like 0.5, then what that means is that this friction force should be exactly half the magnitude of this normal force. See how this is half of this? Right? Like this, what do I draw here? I made this one almost 4 centimeters long. This one's about 2 centimeters long. So there you go. Half. Versus the one on the right, if you have a coefficient of friction of exactly 1, that means the friction force is exactly the same magnitude as the normal force. Right? It's like a 1-to-1 ratio. Now, I want to go another step of this. I want to relate this back to the first step that you guys learned before all this force stuff, which is kinematic motion. Which car do you think is going to slow down faster? Obviously, the one with the anti-lock braking system. And that's the whole point of trying to take advantage of the static friction. So let's see if we can quantify somehow what that acceleration would be. We did that. Let's go to Newton's second law of motion. Okay, guide you guys through this very short proof. Newton's second law of motion says that the net force will accelerate the car rate. F equals ma, right? I really prefer the fraction form. Acceleration is net force divided by mass, but I'm going to make some substitutions so it's look a little bit cleaner in the notes. Okay? Now the net force. Hey, what is the net force on either one of these cars? It's which force? The friction force. Because the other two cancel out. You guys see the weight down and the normal force up? Those just balance out, don't they? Like tip to tail, goodbye. Right? So there's no vertical force net. Right? There is a horizontal force, and that is the net force. So this right here is the friction force. This is force due to friction. That's causing the car to accelerate. and I'm using acceleration, accelerate in a physics sense, right? In this case, like slow down, but it's like a rate change of velocity. The friction force, you guys have a formula for it. It's just coefficient of friction times the normal force. Well, that's always true in the kinetic case, so the car is sliding to a stop. For a static case, remember it builds up to that point. Let me remind you guys why it builds up to that point. You guys saw this yesterday. You guys remember if I hook a spring scale to a weight, okay, and I start pulling, oh, look at that. See how for the first few newtons, this doesn't move at all? Okay, so it's like that force is building up, building up, building up, and the friction force is constantly just counteracting the number of newtons that I'm pulling. This is rating some number of newtons, okay? But at some point, it'll break that friction and it'll start sliding across. But it can go up to some value. That's why this is an inequality. But let's assume that this computer system, this anti-lock braking system inside the car, accounts for that and is somehow able to maximize the value of coefficient friction. So we'll go ahead and let this be equals. Right? Let's say the computer system took care of all that. Okay. Wouldn't that mean that this friction force is equal to coefficient of friction times the normal force? Right? Because that's just the equation I just showed you guys. This is equal to this, like at a maximum. Okay. So this is the maximum. This would be the way to slow down the car maximally. Okay. Slowing down the car, we're really solving for acceleration, right? What's the rate that the car can slow down? I want to solve for A. Okay. That's our goal. Okay. I'm going to make one more substitution. Look at this normal force. If it's a level road, nothing fancy going on, what is this normal force also equal to? 9.8 meters per second squared times the mass of the car. That's the weight of the car, isn't it? Okay. That's true for both free body diagrams. If the normal force is exactly balancing the weight. Okay. So I can substitute here. I can say the normal force is actually the weight of the car, which is mg. Okay. We're still trying to figure out what is A, what is the acceleration of the car, at what rate is it slowing down. Okay. This line. Do you guys see what variable is going to cancel right here? The mass of the car. Goodbye. I see it's going to cancel out on both sides. You can divide both sides by m. Okay? That means something. Anytime you guys see a variable cancel out in physics, which happens quite a bit, it means that the magnitude of that variable does not matter. So how about this? Let's say this guy drives to the grocery store. He has an empty car. He drives to the grocery store, fills it up with a bunch of groceries. Maybe he's getting ready for the next pandemic. It's just all full. Right? Drives back to his house. The fact that he has lots of groceries in his car, is that going to change his stopping distance if he has to brake in a hurry? No, has nothing to do with it at all. Or actually, here's another classic physics question. Let's suppose you have a little tiny sports car side by side with a big old semi-truck. And other than the mass, of course, their masses are wildly different, but everything else is the same. Let's say they've got the same brand tires, they're on the same road, they have the same starting speed, and they both slam on the brakes at the same time. Okay? Which vehicle, the little tiny sports car with a big old semi-truck, is going to stop first? Yeah, same stopping distance, same time, because they'll have the same acceleration, they'll have the same like slowdown rate. Okay? And that slowdown rate is just the coefficient of friction times gravity. Okay? That's it. The mass of the car, mass of the vehicle actually cancels out. Okay? I could have done that the same thing with the kinetic, like the sliding case. I'll just do ... because the mass is the same. You got coefficient of kinetic friction times gravity is equal to the slowdown rate of this car. Okay, so there you go. Okay, so that's the physics behind anti-lock braking. You can take advantage of coefficient of static friction, which will give you a faster slowdown rate. Okay. There we go. Let's flip over to. Oh god, share my screen. Oh, hold on. Get down here. Stop. Present screen to share PowerPoint. This one, present, no, okay, present. Okay, here we go, free body diagrams. So you guys saw this yesterday, here this was defined. I'll go through these first few slides pretty fast. Just remind you guys here again from yesterday. So free body diagram, you're only drawing force vectors. And there's a certain convention how to draw these. So draw a center mass dot, and then all the force vectors extend from that, make them proportional, all that stuff, right? So block that rests on table has a weight acting down and a normal force acting up. Boom, boom, done. What if you're pushing it horizontally, but it hasn't broken the friction yet, just like I showed you guys a moment ago? Okay. Well, maybe there's an applied force and a friction force that are also balanced for the block to be at rest. I mean, at rest is one example of equilibrium. Does equilibrium necessarily mean at rest? No, equilibrium just means there's no net force and there's therefore no acceleration. But if like cruise control, constant speed up I-95 going constant 70 miles an hour, that is also an example of equilibrium. There just has to be no net force. Right? That's like this next one right here. Right? So let's suppose you're pushing a block horizontally and it's moving at constant velocity. So there's a pushing force and there's a friction force, but they also balance out. Look at that. Right? In fact, if all you had was just this free body diagram and you weren't told if this friction was static or kinetic, then it would be ambiguous as to whether it was in motion. It looks exactly like the previous free body diagram. Right? Now, if you're told this is kinetic friction, you're like, okay, well, it must be sliding. So, right? But that'd be the only way you would know. What if you push it so there is a net force? Well, it might look like something like that. There'll be one possible solution. Right? Rock and free fall. Boom. That's it. Right? Rock and free fall. The only force it's under the influence of is its own weight. And if you go back to Newton's second law of motion, divide by its mass, you get G, the free fall rate for acceleration. What if there is air drag? Ooh. So this is, I think maybe the first time I brought this in class. What if there's air drag? So now the net force is not its own weight. It's less than its own weight. You divide by its mass, you'll get an acceleration that's less than the full free fall rate. I asked you guys to model this. Could you figure out what the V versus T graph would look like? This is yesterday's notes, and just to remind you guys. I told you guys a little bit about drag force. I wanted you guys to see that it was, that if you increase the speed, that you'll increase the drag force. So as this thing's falling faster and faster, it gets the air, the drag force first builds up more and more. And at some point, it reaches what's called terminal velocity. So it actually goes into equilibrium. The drag force will eventually build up to its own weight. And at that point, it'll go down at constant velocity. So V versus T graph, the classic V versus T graph that we did with kinematic motion is just a straight line with the slope of G. But if you include the air drag, it's going to bend down like this and eventually reach terminal velocity, which would be a good thing, especially for like if you jump out of a plane with a parachute. Right? Why do you want your parachute to be really big? Well, because cross-sectional area also influences the drag force, right? You guys remember that? Figure that out. Right. Hold on. There's a way how to do this. Flip this back to figure out how to solve this problem. Right, then flip back. Then present. Okay. That's the next slide. We're just talking about this. What if it keeps picking up speed and eventually reaches terminal velocity? That's the point that the drag force is matching the weight. Okay. Now it's not going to speed up anymore. Because again, that would be equilibrium, goes down, constant speed all the way down. Boat moving through water, got weight, buoyant force, say a propelled applied force and a drag force that balance out as long as it's constant velocity. That's how you know they balance out. Equilibrium. Challenge question, can you draw three forces to put something in equilibrium? Right. There's a couple solutions to that. Right. Parachuter before terminal velocity, parachuter at terminal velocity, right. Below the drag force. Here's the last slide that I showed you guys yesterday. A rocket just screaming through space, 10,000 meters per second. What are the forces on that rocket? And the answer is in front of you right now. That's it. Right. What's keeping that rocket going? Inertia, just inertia. Just like Voyager spacecraft. Right? There are no forces. Remember that all velocities are relative anyway. Right? So how fast is something moving? Well, it's relative to something. Right? If this rocket did turn on its booster engines, then wouldn't there be a net force? And it would accelerate, which would break this condition that says constant velocity. Right? So there are no forces on that rocket. Okay. Here's the new slide. Now we're picking up. Air hockey puck moves across the surface at constant velocity. Can you guys draw the free body diagram for that? I'm going to glance around the room. I wonder how many guys are going to be able to get this. See if you can get this in your notes. Had a few students who were able to get this last class. So air hockey puck moves across the surface. You guys have played air hockey, right? I'm going to use this as a proxy for like a zero friction situation. It's a really good model for that. So think air hockey, think no friction. There are some forces. I'm just going to figure out what this free body diagram looks like. Free body diagram. Almost. Brindley got it. Right, so Brindley got it. Who else is going to get this? Yeah, and Luke got it. All right, so what you guys are saying is this air hockey puck has a weight that's pulling it down. There's the force from the air jets holding it up, kind of like the normal force, right? Think like that. Right? And that's it. That's all the forces. Right? One force down, one force up. In fact, if you were looking only at that free body diagram, which only includes those red vectors, would you even know if that air hockey puck was in motion or not? No, you'd have no idea. Again, because velocity vectors are relative anyway. And if you're sitting in a plane or a car, you don't know how fast it's moving. You can't feel that. So that's it. One force down, one force up. Same as if it was at rest. Equilibrium. Ooh, the Earth and the Moon. Yeah, can you guys draw a free body diagram for Earth and the Moon? Earth and the Moon. Is the Earth pulling on the Moon? Yeah, that's what's keeping it in orbit, right? Is the Moon pulling on the Earth? Yeah, it might be why we have tides, or that's the main driver of the tides, right? The Moon pulling on the Earth. Okay. But which force is bigger, the Earth pulling on the Moon or the Moon pulling on the Earth? For every force, there's an equal and opposite reactive force. Equal. Wait, hold on. Are the Moon and the Earth really pulling on each other with the same force? The same force? Yes, they are. But which one undergoes a greater change in state of motion? Definitely the Moon. Yeah, the Earth might wobble a little bit because of the Moon, but the Moon is definitely in orbit around the Earth. Why? How is that then? If they have the same force on them, because the Moon has much less what? Mass. That goes back to Newton's second law of motion, right? Did you guys draw that right there? Earth pulling on the Moon, Moon pulling on the Earth. It's like two separate free body diagrams. Let's flip over to my projection screen. I want to convince you guys that that's actually true. That for the Earth and the Moon. Okay. So you have a big old planet, little tiny moon, like that. I'm going to represent these masses in terms of like lab weights. So let's say I have a planet, mass is represented with the lab weight, and then the moon is lab weight. We'll start with a very basic situation where maybe they're the same mass. Okay? Let's call them the same mass. Because if they were the same mass, then wouldn't it be really obvious that the forces would have to be equal? Right? There's a force there, there's a force there. Right? It's a gravity pull. In the future, we'll talk about where we'll talk about universal gravitation. Okay? So force that way, force that way. Okay? It's definitely equal and opposite. Okay, so that makes sense. But what if you started to increase the mass of the planet compared to the moon? Okay. Let's do this. Okay. So I can represent that by throwing in maybe some more lab weights to represent an increased mass. More of these guys. We'll click on that. Okay. Well, wouldn't each new lab weight also attract to the moon lab weight? So it'd be like this. And then this one would pull like this. Like that. Okay. And if you didn't see it before, I bet you definitely see it now. Yeah, the forces do have to be equal and opposite. It's like 3 units from the Earth to the moon and 3 units from the moon to the Earth. Okay? So it doesn't matter if objects have different masses, right? Or however they're pushing or pulling against each other. Okay? Forces are always equal and opposite between two interacting objects. By the way, do you guys know a YouTube channel called Veritasium? It's a really good science channel, Veritasium. So I actually stole this idea from one of those old videos. Let me go back and present. Gotta present my screen for this. Oh, come on here. Present screen to share. All right, we're back to here we go. Roller coaster. So this slide and the next couple slides have to do with this roller coaster. Well, we'll start off real basic. Let's say a roller coaster is at the top of the hill and it's just like basically zero velocity. I bet you guys could do this. You could say, well, that coaster has a weight pulling down, and then there's a normal force from the track holding it up. Okay. And if it's pretty much zero velocity, then shouldn't those forces just balance? And okay, so that's all fine, right? Now here's where it gets tricky. We're gonna look at a couple other situations in that coaster motion. You guys are gonna learn some new concepts here. What if that coaster is down at the bottom of that track and it's in motion? So I'm representing its motion with that green velocity vector, which is not actually part of the free body diagram, but it is going to affect the free body diagram. Okay? So here's what you're looking at. This coaster is in a part of this valley that is actually curved. See how it's curved? And because it's on a curved track and it is in motion, as it moves forward, it doesn't actually go straight forward, does it? Isn't forced to go up? Doesn't the track force it to go up? Huh. So the free body diagram for this, see, it's gonna have a weight that pulls it down. Okay, just like there's the earth pulling on the coaster. Is there a normal force from the track? Yeah. Do you guys think that this coaster is going to be in equilibrium though? It is not. There's actually a greater force. The normal force is actually more than the weight of that coaster car. What that means is that as that car moves forward, it is going to be forced upward. There is a net force upward, and that would force it into the loop, wouldn't it? Wouldn't that force it into the loop? The net force between these two, the normal force up, say you subtract the weight down, or put these tip to tail, and there's going to be a net force. You could call that net force the centripetal force. So that's a future topic, but that has to do with like rotating motion. I said eventually we'd get to the case of, say you're in a car. Remember 3 ways to accelerate a car: hit the gas pedal, hit the brake, and then turn the steering wheel. I said we'll eventually do bringing the steering wheel. Ooh, this is kind of getting at that idea, isn't it? Okay. Let's do one more roller coaster scenario, and this one's real tricky. But I wonder if some of you guys are gonna get this. So let's say this roller coaster is continuing its journey. It's now at the top of the loop, and it's definitely in motion. In fact, it better be in motion, right? Because if it weren't in motion, wouldn't it just want to fall right off the track? Right? So I bet it. I hope it's going some minimum speed to get around the track. That's actually another really good physics question we'll do in the future. Is what is the minimum speed to get around that track? Maybe if you knew the radius of that track of that curve, okay? Or here's another question related to that. I wonder if there's some minimum height of this hill that could allow it to have a speed so that it could at least barely get around the track. But for now, let's just look at the free body diagram. Like kind of glance around the room. Like I said, this one's really tricky. I wonder how many guys are going to get this. What are the forces on that car at exactly that point? What are the forces on that car? Yeah. For this version. All right, he's gonna get this one. Yeah, so Carson got it, Brindley got it, yeah, Rebecca got it. I'm impressed that you guys are getting this. This was pretty tough. See if anybody else is going to get this. Not close. Oh, yeah, Addie got it. Almost. Yeah, that was right. Joshua got it. And, oh, that's right too. Yeah, Isabella got it. And I think Ernie got it. Oh, wow, a bunch of you guys got that. I'm really impressed, so good job. Right. So this cart has a weight that's pulling it straight down. So that's their Earth's pull on it. Isn't there also a normal force from the track? But which way does that normal force also point? Down. The track is pushing that car down. That's it. That's the entire answer. So would that car be in equilibrium? Definitely not. There's definitely a net force, and that net force is downward. Now, if you were riding along inside that car, let's say you were blindfolded, what you would feel, you would feel like you were being thrown upwards, wouldn't you? That's what you would feel like is going on. Now, there's a whole story attached to that. It has to do with like a rotating frame of reference. You would think that there's what's called a centrifugal force pushing you upward. That literally means center fleeing force. But from an inertial frame of reference, say us from the side, we're looking at this thing, there actually is no force that points upward. There's only forces that point towards the center of the circle, and that's called a centripetal force, like center-seeking force. Right? And a key to make this happen is that the cart is in motion, so it has to be in motion for the solid workout gets around the track. Okay? So yeah, really tricky one, but some of you guys figured that out. Awesome. A car brakes to a stop. Hey, we just did this one a few minutes ago. So this car has a weight down. There's a normal force from the road holding it up. And if it's moving to the right, then the friction force is to the left. How many guys can eyeball that free body diagram and estimate what the coefficient of friction is between the tires of the road for that car? What's the coefficient of friction? Yeah, Josh?
0.5.
About 0.5. That'd be a pretty good estimate. And that's because this friction force is about half the magnitude of its normal force. Is that? So friction divided by normal force. About 0.5. Yeah, good call. A car goes around a curve as seen from behind. Let's say we're looking at the taillights of this car. It's got a weight down. It's got a normal force up. And then, now, why would it be going around a curve? Well, there's actually different possibilities. So if it's on a banked curve, then you might say, well, maybe it's the horizontal component of the normal force from the banked road. Right? If it's a flat road, then it would just be friction. Friction is the only thing that's going to allow it to go around the curve. So I might throw in a friction force. A block hanging at rest from a spring attached to the ceiling. Ooh, block hanging. Did you guys draw a weight of the block is acting down, and there's probably a spring force holding it up? And if it's at rest is one example of equilibrium. So see how the forces are balanced? Now here's where I want to flip the screen and give you guys some more notes. So we're talking about springs now. We're bringing in springs. I want to give you guys notes on something called Hooke's Law. Hooke's Law. I'm going to write this out. So Hooke's Law. Okay. Hooke's Law will tell you force on an ideal spring. Some textbooks write this: force from a spring is equal to negative kx. Okay. I prefer to think of the force on a spring. I usually write it the way I'm about to do it right now. Force on a spring is just equal to kx, so I can just drop the negative sign. Okay. So say if you push on a spring to compress it, or if you pull on a spring to stretch it, either way, there's some kind of force involved. You have to put a force on the spring to change its length, and the spring puts an equal and opposite force back on you. Okay, so could be either way. So let's take a look at this version of it. Let's do the force on the spring. Now, Hooke's Law, we're talking about an ideal spring. So this would be for an ideal spring. But all the springs we're going to be working with in here are going to be ideal springs. What do these different parts mean? I mean, obviously F is a force, but what is K and X? So let's draw the situation out. You guys saw spring hanging from a ceiling. So I'm going to make kind of a wide ceiling so I can get two of these side by side. Well, maybe like a before and after. So maybe there was a spring and it started out like that, and this was unstretched. So I'll have this be an unstretched spring. Just hanging out. There's no force on it. It's just some natural length. Then I'm going to attach one of these lab weights to it, and it's going to stretch it. It's going to stretch it. It might look something like this. Something like that. Because I hooked one of these lab weights to it. Got some mass, got some weight. Okay. And look at how much it's stretched as a result. From there to there. Okay. I'm going to call this stretch value X. Okay. Some textbooks do delta X, like a change in length. I just do X so that I think it makes the equation look a little cleaner. Okay. So X is equal to how much the spring has been either stretched or compressed. Because you could also push on the spring, like squash it, and then Hooke's law would still apply as long as ideal spring, all that stuff, right? What the negative sign means is that the spring is trying to do the opposite of whatever force you're putting on it. So if you displace it, say down, doesn't the spring pull back up? And if you were to compress it by pushing up, wouldn't the spring push back down? That's what the negative sign's about. But again, I just care about the magnitude, so it is. And what the K represents is called the spring constant. Think of it like a stiffness. Like how stiff is that spring? Because different kinds of springs will stretch differently depending on how much force you put on. And you guys know that because you guys got your hands on some spring scales the other day. That's where the different spring scales. We'll calculate this the spring constant for a couple of these here in a minute. Some of these had a really loose spring constant, or very low spring constant, like this green one. Some of them were really stiff, like this gold one. Like, needs lots and lots of force to pull it. Right before I do that, though, I want to make a graph with you guys. Let's graph this right here. Let's graph what is the force versus, say, stretch amount. So pick some axes. I'm going to put how much it stretches, or compresses for that matter, in meters on the horizontal axis. Let's say what's the resulting force, or what's the force on the spring in newtons. So 0 force at 0 stretch or compressed amount, like the unstretched one. So there's your point right there. And what is the rest of this graph going to look like? Do you think it's going to be a straight line or a parabola? What do you guys think? Does that look like a direct relationship, like y equals mx, f equals kx? It's exactly what that is. Straight line. Where the slope of this is, if you guys are following, what is the slope of that? K, yeah, it's a spring constant, right? So the more you stretch it, like if you stretch it across as far, it would require twice as much force to do that. Yeah. Oh, like I said, let's calculate the spring constant for a couple of these springs. Bring out these two, the one with the small spring constant, one with the largest spring constant. Yeah, go ahead. All right, so check out. All right, so we're looking at, let's do the green spring scale versus the gold spring scale. Did you guys happen to notice that, I mean, maybe this was so obvious that you didn't really think about it, that the spring scale, the number of newtons reading on it is scaled linearly, like 0 newtons, 1, 2, 3, 4, 5 newtons. See how it's like scaled linearly? The reason for that is like, well, if you stretch it twice as much, it's reading twice the force. It's scaled linearly for the same reason that this graph is a linear graph, right? So everything scales linearly. Okay. So let's go to F equals Kx. And we're going to solve for what is the spring constant on this green scale. Okay? The spring constant. Well, I know the force readings because it says how many newtons on it. Let's stretch it all the way up to 5 newtons. That's right there. That 5 newtons. I'll plug in 5 newtons. Is equal to, okay, so some spring constant we're solving for, multiply by, well, what is the distance for that 5 newtons? Break out the ruler. That looks like 5.2 centimeters. 5.2 centimeters. So this is 5.2 divided by 100 meters. That be true in terms of meters? Divide by 100. Okay. I'm gonna do some algebra. Divide both sides by 5.2 over 100. So it is 5 divided by open parenthesis 5.2 on 100. Can isolate K. So K for the green spring scale is 96 is the number on the calculator screen. And then the units would be newtons per meter. Newtons per meter. Hey, just like you know what those units are, newtons per meter. That's exactly consistent with the rise over run of this force versus distance graph, right? Newtons per meter. Is that rise over run? Right. How about the Gold spring scale? Okay. Remember, this one has a really stiff spring. It's really hard to pull this. Okay. It goes up to 50 newtons. That's 50 newtons right there. Okay. So, same setup, F equals kx. We're solving for k, but now this is the Gold spring constant. Goes up to 50 newtons. That's where it maxes out. Equal to k times. Okay. Now this one's scaled slightly differently too. So that is a distance of 6.2 centimeters. That's 6.2 centimeters. So that's 6.2 divided by 100 meters. Because centi is 1 over 100, like 100 cents in a dollar. So take my 50 newtons. Force divide by open parentheses 6.2 on 100. That many meters stretch to get there. Okay. Look at, ooh boy, look at the Gold spring constant is 806 Newton per meter. Wow, that's much different than that Green spring scale. But you guys knew that was going to happen anyway. Look at that, it's like 8 times as stiff. Wow. Called Hooke's law. You guys good with Hooke's law? There we go. Right. So flip back over to computer. I have to present. Oh, hold on. I gotta close that. Close that. Okay. Okay, let's switch this back. Then I have to present screen to share, flip this back. Rocket free fall, hold on. What we're doing, springs? Wait. Where's the spring? Oh, this is yesterday's stuff, isn't it? Oh yeah, we did this. Here we are. Okay. So you guys just saw this. Right? Now you guys are seeing equilibrium because it's at rest. Right? Do you guys think if you put a larger weight on there, say you took off that weight, you attach a large weight, it's going to stretch it even more? Yeah, it definitely would, wouldn't it? But it probably that would also increase the spring force because F equals kx. That increase that directly proportionally, and then there would be a new equilibrium. Next one, bottle rocket blasted upward through the air, and there is air drag. Ooh. So different possible solutions. This one, maybe there's a weight pulling this down. There could be a thrust force acting upward, and then also a resulting drag force. And I told you, like an additional bonus equation from that yesterday. There's one possibility. Now, the free body diagram that I have up there right now, would that bottle rocket be in equilibrium, or would it be accelerating? What do you guys think? Yeah, accelerating, because you see how there is a net force, right? Like this thrust force is more than the sum of the weight and drag force acting in the opposite direction. If you connected this all tip to tail, wouldn't there be a still net force upward? Yeah, there would be. Check this here.
Do you need a scale?
I'll get you here. Yeah, okay, you're good. Again, put there. How about a baseball flying? Hold on, how are we doing? First block. Okay, a baseball flying at a 45-degree angle. There is air drag. Think there's a weight pulling straight down? And the air drag points which way? Opposite of the motion. Ooh, look at that. Opposite of the motion. How about, hey, 2 guys pulling a donkey. One guy pulls forward to the left, one guy forward to the right. Okay. So forward to the left, forward to the right. But what if the donkey is not moving? Do you think the donkey's hooves are dragged into the ground? Do you think there's a friction force between the hooves and the ground? Okay. That exactly balances out the forward components of the tension forces. Look, the left part and the right part cancel out, but also the two forward components balance out with the friction force pulling back. Everything balances, everything zeroes out. Block at rest on a ramp. So if it's at rest, then you know, well, it has to be in equilibrium. Let's go through these forces. You guys know there's a weight pulling down, and I've been preparing you guys for this for a long time in this class. You guys know to introduce a Cartesian system that's aligned to the surface, right? Okay. And then break the weight into components, mg is weight. Now we're adding more to the story. You guys know that there's a normal force from the surface, and normal means perpendicular. So look at that, it's perpendicular. It's not straight up, it's perpendicular to the surface. In fact, see how it's actually equal to mg cosine theta? It balances that one out. I did put that on the poster hanging up here. This is equal to mg cosine theta. But if this block is at rest, doesn't it have to be a force that also balances out the mg sine theta? What do you think that force probably is? Yeah, friction is a good candidate, and that's what I did right here. See how that's the same magnitude as the mg sine theta? That could be equilibrium. Next one, block sliding at constant speed down a ramp. It might have the exact same free body diagram. Remember, constant speed, that's also equilibrium, isn't it? So if you didn't know if that was kinetic or static friction, in this case it's kinetic friction, but if you didn't know, it would be ambiguous as to whether it was at rest or not, or sliding at constant speed. What if the block is sliding up the ramp, slowing down? Right, so it's got this way, break down into components just to make more sense of it. It's got a normal force right there. That's equivalent to mg cosine theta. Now this one, which way do you think the friction is pointing now? Opposite of the motion, which is now down to the left. Is this block in equilibrium? No, because there's a net force. There's a net force down to the left. This block is slowing down in a hurry, isn't it? Yeah. Well, okay, Atwood, we'll save that for another day. Yeah, that's exactly what I've been getting through today. So awesome. And we got any physics questions? And I will see you guys Friday.